Hi everyone. Today we will learn about optical isomerism. Optical isomers can exist whenever we have a chiral carbon. A chiral carbon is going to be a carbon that has four different groups attached to it. So let's look at this example that I have written over here and identify whether this molecule has optical isomerism. So when we look at this particular carbon, you see this carbon is attached to three same hydrogen atoms. So they do not have any, this is not a chiral carbon. And if you look at this carbon atom, they have the same situation, three hydrogen atoms. You can see for this carbon, they have two hydrogen atoms. Okay, it's not a chiral carbon. But if you look at this carbon atom over here, okay, if I rewrite this, okay, this carbon, you have the Cl and I have the CH3 and I have the Br, and this entire thing I write it as C2H5. Okay, so I put it like this, C2H5, and you can see very clearly now they have four different groups attached to that carbon. Therefore, okay, that carbon is known as a chiral center, okay, or chiral carbon, okay, a chiral center or chiral carbon. Now, this chiral center, this is going to tell us that this particular molecule will exhibit what we call as optical isomerism. Okay, let's actually look at how can we draw optical isomerism over here. Okay, so let me paste the image over here. Now, what we can do over here is, okay, the optical isomerism is going to be, they have another isomer that is going to be in mirror image to this particular arrangement. So to draw that is quite easy. Okay, so you just put the carbon over here. So we have Cl, so we just put the Cl, and we have C2H5. Okay, so we just put over here C2H5, just a mirror image. So you have something like this. You have the Br, and then you have the CH3 over there. So this is going to be how we draw, okay, the optical isomerism, okay, for the set of optical isomerism for any compound that has a chiral center. Now, so generally, what is optical isomer? Okay, optical isomer is going to be a type of stereoisomer apart from your geometrical isomer that we have learned earlier, which is going to be cis and trans. These are going to be optical isomer, which is going to be, they have the uh, same atoms, okay, being attached to the molecule, but they are going to have different arrangement in space. But okay, they are going to have, okay, different chemical property and physical property. In this case, for optical isomerism, okay, they have the same chemical property, but the only thing that is going to be different over here is going to be their physical property, which is going to be the ability or the effect that they have on polarized light. So what is going to be polarized light? Okay, so whenever we have a normal light is going to be unpolarized. So they have electric and magnetic fields which are vibrating at 90 degrees, a right angle at all directions. You can see in this diagram over here. Okay, so this is going to be normal light. Okay, so we are going to put them into polarizer where they can actually polarize the light. Okay, so this is going to be a polarized light. So the polarized light is going to be where your electric and magnetic field is going to vibrate in a single direction. So when we put this into our optical isomer sample, okay, they do exist in form of a mixture of 50% and 50%. So they are going to be in a mixture. So when we put them, okay, this optical isomer, they are going to rotate the polarized light, okay, into different direction. So you can see if you going in this direction, you can see that this particular molecule, they rotate it, okay, in somehow in a clockwise direction. And here, okay, you are going to see that this is going to be rotated at the anti-clockwise direction. So this is going to be how, okay, the optical isomers differ in their effect in polarized light. Now, so it is important to learn how to draw, okay, how to show the optical isomer using the mirror image method. Okay, so we need to draw the mirror. Okay, so somewhere here, okay, and then we try to have them arranged in a try to draw, okay, the perfect mirror image of the sample. Now, so now if we want to identify whether the following has optical isomer, the important thing is to identify whether they have a chiral center. So let's look at the chiral center or the chiral carbon. So if I use, okay, the red pen over here, I'm going to take, okay, this carbon is not a chiral center attached to 3 hydrogen groups. Okay, you can see in order to have, okay, the chiral center, they must have 4 bonds. So this is going to be, there is a double bond there, cannot. And this carbon also, there is a double bond directly attached over there, cannot. You need 4 different groups. Okay, so the only thing that is left over here is this carbon. And you can see this carbon, okay, is a chiral center. Why? This is going to be a different group. This is going to be a different group. This is different group. This entire thing is going to be a different group. So therefore, there is a chiral center. Okay, so this molecule can exhibit optical isomerism. So let's look at this carbon. The second example, no. Okay, no, no. Okay, so let's look at this carbon. Also no. Why? Because there's 2 same groups, or to be exact, 3 same groups. Not possible. Okay, there's no other carbon, so they do not have any optical isomerism. So let's look at this carbon. No. Okay, this carbon, no. Why? 2 same Cl and also CH3 cannot. Okay, this is also cannot. So they do not have any optical isomerism. So let's look at this example. This carbon, no, because all there are 3 hydrogen atoms. This carbon also cannot because there are 2 hydrogen atoms, cannot be the same. Okay, if you look at this carbon, okay, we can see that 3 hydrogen cannot. Okay, but if you look at this carbon, okay, you have 1 hydrogen, 1 group, another group. This entire thing is going to be 1 group, and you have this as 1 group. So if I want to draw, okay, the optical isomer, okay, let's select 1. So let's select this molecule. Okay, let's actually try to draw, okay, the optical isomer for this molecule. Okay, so let's draw. So for example, now when I represent this, the best way is to write down carbon. Okay, so you have Cl. Okay, so please take note how I draw over here. So I put, okay, 2 same lines. Okay, so it's going to be arranged in a tetrahedral shape. So this is going to be C2. You can see, or if you want to write down C double bond C, and then there is H, and then there is H over here, and then there's another H over there. And we have, okay, another Cl. So I put over here. So I put maybe H, doesn't matter. Okay, H, and then Cl, dotted line, Cl. Okay, please take note, 2 of them have the same line, and then 1 is going to be protruding, coming out from your screen. Another one is going to be a dotted line to tell us that it is going to go behind the screen. So if I want to draw, okay, the mirror image of this, so again, carbon, so I have Cl, okay, dotted line, okay, Cl, and then this one is going to be hydrogen, and this one is going to be C double bond C, so hydrogen, hydrogen, hydrogen. So this is going to be how do we draw the optical isomer. So the concept over here is we need to make sure that we identify the chiral center, and we can conclude that they have optical isomer, and then what is left is just to draw them. Yeah. So that's it, guys. Thank you. Bye.